You've seen this button before, the logarithm. But how did that button get onto the calculator? We know that the logarithm is the inverse of an exponent, but it wasn't always that way. And the story behind logarithms is one that reshaped math entirely. Ever since the time of the Babylonians, people had been interested in the idea of repeated multiplication. Although the concept of logarithms and exponents were not established, people were in a sense asking, what exponent do you need to raise a base in order to get a desired power? The solution to this was regarded as a cool idea, but the usefulness was not fully realized until the 1600s. During the late 1500s, astronomers were conducting massive calculations to learn more about planetary motion. Times haven't changed, and people back then didn't like manually calculating massive multiplications. One popular shortcut was the method of Prosthaphaeresis, basically the use of trigonometric identities. Say we were multiplying 866 by 500. To solve this using Prosthaphaeresis, we would need to convert 866 and 500 into sine functions. And once we do that, the answer would be a matter of finding the resulting trig functions, performing some subtraction, and dividing by 2. The sine of 60 is about 0.866, and the sine of 30 is 0.500. Notice they are 1,000th of the desired value. We'll worry about this later. For now, if we plug in 60 degrees for A and 30 degrees for B, then we need the cosine of 30 degrees and the cosine of 90 degrees. Cosine of 30 is around 0.866 and cosine of 90 is 0. Now just divide this by 2 and we get 0.433. Now, to get back to our original equation, we just need to multiply both sides by 1,000,000, giving us our answer. Obviously, for this method to work, one would have to know their trig functions. And at the time, trig tables were well calculated and documented, so this would just be a matter of plugging in numbers and readjusting. But as you also saw, Prosthaphaeresis took a lot of work. In the 1600s, John Napier came up with a new idea. Instead of using trigonometric functions and identities, Napier decided to use a relationship between a linearly increasing quantity and a proportionally decreasing quantity. To understand what Napier did, let's create an arithmetic series and a geometric series. The arithmetic series will start at 2, and let's give it a difference of 2. It doesn't really matter what we pick. For the geometric series, let's start at 3 and give it a common ratio of 3. Now, say we are multiplying 9 by 27. We know that 9 corresponds to 4, and 27 corresponds to 6. If we add 4 and 6, we get 10. The term in the geometric series that corresponds to 10 is 243, which happens to be the product of 9 and 27. Multiplication became simple addition. Now, what about division? Let's divide 729 by 81. 729 corresponds to 12, and 81 corresponds to 8. 12 minus 8 is 4, and 4 corresponds to 9, which is the quotient. Division became subtraction. And you can go even further. If you want to find a root, you can just divide. The cube root of 729, just divide 12 by 3, and that's 4, which corresponds to 9, the cube root. You may notice the pattern. These are the same rules we can use to simplify modern logarithms. Obviously, we don't define logarithms like this today, but the idea is still there, and the rules still apply. Also notice that if we switched up the arithmetic series or the geometric series, we would still get valid answers. As long as we have a table that links the two together, we're all set. So how does this tie in to Napier? Well, Napier imagined two lines. One is finite, and the other is infinite. Both lines have a particle on them that begin by traveling at the same speed. But as they move along, particle 1 slows at a rate proportional to its current position. Think of this like a decreasing geometric series. Particle 2 continues traveling at a constant rate, which you can think of as an arithmetic series. Notice neither particle will arrive at its destination. Particle 1 slows infinitely, and line 2 has no end. The connection between the 2 points at any given time was what interested Napier the most. The distance traveled by particle 2 was called the logarithm, and the distance left for particle 1 to travel was called x. Now, astronomers using Prosthaphaeresis in the 1500s essentially had their tables built for them because the technique used well-documented trigonometric functions. But Napier's method was new, and remember, in order for it to be effective, one had to know the corresponding terms. But no such tables existed yet, so Napier had to construct his own tables, which is how he spent the next 20 years of his life. After years of grueling and tedious multiplication, at long last, Napier created massive tables containing thousands of numbers, which he called logarithms, or ratio numbers. As you know, Napier's idea of logarithms differs a lot from what we know today. Napier didn't think in terms of bases or exponents, but what mattered at the time was that the calculations worked, and his discovery was immediately applauded and accepted. Astronomers and mathematicians had been waiting for an update to Prosthaphaeresis for years, and now it had finally come. Multiplication that once required hours can now be simplified in mere minutes. One fascinated geometry professor named Henry Briggs was so impressed by these logarithms that he decided to visit Napier in person. While Napier's current logarithm table worked and was effective, it was not very intuition friendly. The logarithm of 10 to the power of 7 was 0, and many other logarithms were huge numbers. This was due to the fact that at the time, many decimal numbers were scaled up. So during their meeting, Briggs proposed a new idea. One way to think about Briggs' idea is that he suggested to use 10 as the common ratio for the geometric series and starting where the logarithm of 10 equaled 1. Briggs effectively came up with the idea of a base, and this setup was far more straightforward. Napier approved, but he was getting old and soon passed away at the age of 67. Alone, Briggs set out to create some tables of his own, and after a couple of years, with some additional contribution by Adrian Vlack, mathematicians could now enjoy a functioning table with 100,000 base 10 logarithms. And for the next 300 years, this logarithm table remained virtually unchanged, with only minor tweaks and corrections. Briggs effectively established logarithms that were defined by bases, the same concept that we hold today, and the way that we now teach logarithms. Logarithms began as an endeavor to simplify mathematical calculations. It took years of trial and error for the technique to become fully refined and effective. From trig identities, to Napier's logarithm, to the basis that we have today, that button on the calculator is there for a reason, and we should appreciate it. If you enjoyed this video, be sure to hit that thumbs up button down there, subscribe if you haven't already, and also let me know what videos I should make next. And also, be sure to check out this video right here.